Welcome. In this session, I'm going to talk about continuous annuities or continuous income streams. You might have seen regular annuities in Math 1130 in section 5.4 in our textbook. Regular annuities where you have some payment made periodically, every month or every year. So there we assume that we have a noticeable amount of sum which is paid at regular intervals. A continuous income stream, we assume that the income occurs most of the time rather than coming in big separated chunks. So think about something like a retail business. Customers walk in all the time, you get some revenue, so it's more or less spread out. To describe the income for such things, we have to give them at some rate per time period. So on average, you get so much per week or per month or per year. In our mathematization, we will assume that things are given at annualized rate. Income can vary over year. A lot of businesses have seasonal variation in income or revenue. So what we have to do is take the rate over some small period of time and then give it as an annualized rate. If there is no seasonal variation, you get the income at the same rate throughout the year. This is what the income will be. So mathematically, we assume that we are given a function f of t. And f of t is the annualized rate of income at time t. If things don't actually change, then f of t will be the income over the whole year. But things do change, so f is not a constant but some function. Which means that to make use of this, I have to think like this. If I take some small interval of time at some particular moment, then the income is the annualized rate times the length of time expressed as fraction of a year. So mathematically, I get f of t times delta t. Now, if you take a long period of time, you can divide it up into small intervals. In each interval, pick some instant ti, and at the length of the interval will be delta ti. Then the income for the ith interval will be f of ti delta I, and for the whole time period, I have to take the total. This is a Riemann sum for the integral of f of t over the time period. So this gives us the integral of f of t dt over the time interval as the mathematical version of the total income. So this is the nominal income because it ignores the time value of money. It ignores the interest rate. Now what if I want to take the interest rate into account? If I want to know how much it's worth in present dollars or how much it is worth if I just bank it, that's the future value. It corresponds to present value or future value of an annuities. So we'll assume that the present value is the value from the current moment, thought of as t equals 0, to the moment whatever. To match the compounding frequency, we'll assume that we are using continuous compounding. So let the R be the rate for continuous compounding. Then the income for some small interval of width delta ti around the instant ti, we know is f of ti delta ti. Present value has to be discounted for the interest rate, and from continuous compounding formula in section 5.3, discounted value is e to the minus rti times f of ti delta ti. This total is the Riemann sum for the integral e to the rt f of t dt. So this is defined to be the present value of the continuous income stream. For the future value, then you just calculate the total future value or the amount on this at the continuous compounding rate of R. From the compound interest formula, this is the present value multiplied by e to the R capital T, the length of the time period. This gives us the future value formula. Making use of these formulas mean that they give you f of t and you calculate this integral. Although we cannot really calculate the integral except in some special cases with only what we know. So a simple situation like in this example can be handled, but not anything more complicated. The convenience store is expected to produce an income stream equal to this amount. So the idea here is that currently it's producing an annualized income of $85,000. We expect that to increase at 2% a year overall. That's what the e to the 0.02t factored means, it means we expect the income to increase at 2% a year. If the interest rate is 3% compounded continuously, what would be the present value of this income over the next 3 years? In this case, f of t is the given function, 85,000 e to the 0.02t. The interest rate is 0.03. It's the nominal rate expressed as a fraction or decimal. The time period is 3 years, so capital T is 3. We take the discount for the interest rate times the annualized income rate, integrate it over the time period. Because we can combine the two exponentials. So the base is the same, I just add the exponents e to the negative 0.03t times e to the 0.02t is e to the power negative 0.03t plus 0.02t or negative 0.01t. It's just a constant coefficient times an exponential. We can just use our general rule for integrating exponentials. E to the power a number times the variable is the exponential divided by that coefficient. Since I'm doing the definite integral, I have to use the fundamental theorem. Evaluate the antiderivative at 3 and 0 and subtract. And if you simplify this, you want the answer to the nearest multiple of $1,000, so round it off to the nearest 1,000, which comes to 251,000.